Hey, I got a thumbs up. All right. Great. All right, today we're going to finish up Newton's laws, 1, 2, and 3. Do some more. The demos I have are for mostly 3. Well, that's the intent. They'll cover the other 2 as well, as we'll see. And remind you that Monday we'll review. Will you please review this weekend? It's always better to review before the test or before you get to talk about the test. The test will be Wednesday. Monday's mainly for you because I've covered everything. It's in the book. Well, as of the end of the day, it's in the book and everything. So Monday is more for you to just iron out some of those confusing parts, or whatever. I'm babbling. You get it. Okay. I want to start with which one? Yeah, let's start with clicker questions. Got some easy ones, some harder ones. Pick a few. Now that you had second law time to sink in a little bit. Oh yeah, I switched it. All right. I'll open polling, and as you dig them out, answer away. A motorcycle undergoes acceleration when? And this isn't to make you feel bad, it's more just so you understand what I'm thinking. I hope at this point this one's fairly easy for most of you. So if it's not, focus on this one. We got 30 responses, that's good. More of you are participating this time than last time. Ten more seconds. 5, 4, 3, 2, 1. All right, 86% of you think B. And a few of you think D. So, a motorcycle undergoes acceleration when a non-zero net force acts on it. The correct answer is, so you can see, is B. So the majority does rule here. If there's a net force and it's not zero, then there must be an acceleration, a net acceleration, and this thing must be moving. A essentially says the opposite of B. Remember that sigma, that's the summation of the forces equals 0. That means there is no net force. It wouldn't be accelerating. And C, equilibrium, means the same thing as A, as the book explained really well. If something's in equilibrium, it's balanced. It's not moving. Or it's not changing its velocity. It's not accelerating. The net forces on it are 0. Questions? All right. I put several in here. What do I feel like? Yeah, you know that one. Let's do that one. Make sure you guys are getting the directions right. It's open. Pull away. The force of air friction or air drag against a falling sack of potatoes. So, sack of potatoes falling, air drag. Does it act upward? Increase with increased area? Increase with increased speed? Or all of the above? This one will give me a clue how many of you are actually reading the book. Ten seconds, because most of you are in. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, we got more of you that time. The majority, 64% of you, think it was D. All of them. And the next best was 20-some% A. Thought it only had to do with upward, not those directions. So you can see the correct answer is D. So why? So most of you agree it acts upward. I hope you do by now. If it's falling, then the wind's blowing that way on it. It's coming into it. B, increases with area. Something that covers more area. There's more air can hit it. That's the rationale behind that. This will receive more air resistance than something with the exact same mass, but with less area, because there's less air that can hit it. So area does matter with air resistance, and speed matters. Speed matters. The faster something is falling, the faster the air is coming onto it. I waited to ask this one after we introduced Newton's third law, because, this, reaches terminal velocity at some point, there-ish. And so it has air drag. There's a force of air acting on the coffee filter. What's the reaction pair to that action? He's right. He said the coffee filter is acting back on the air. The force of the air on the filter and the filter on the air are the same. It's the same force. But that doesn't mean you can't increase it by enlarging the area. Or if you make it fall faster, because it's heavier, 5 coffee filters, it will be falling faster. In order to make it reach terminal velocity, there has to be more air resistance. And there will be. It's kind of cyclical. But anyway, it's all of the above. Questions? Yeah.
So as it's falling, is it also exerting force on the earth and the earth on it?
When it's falling, does it also exert a force on the earth? Not directly, like by contact, but yes, there's something else going on at the same time. This has mass, the earth has mass, and so there is a gravitational attraction between the two, and that is another action-reaction pair. This pulling the earth up, and the earth pulling it down. Notice they're on opposite bodies again? The other pair, this on the air on the filter, the other pair, opposite bodies. Go. When we say that 1 kilogram weighs 10 newtons, we mean that I always take for granted. Cameraman, are you getting the question by chance? Thanks. You've got about half of you. Your clue. Kilogram's a unit for mass. Newton is a unit for force. Weight is a force. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Overwhelmingly B, 74%. The correct answer is B. Good job. It's true at the Earth's surface, because this is taking the assumption into account that we live here on the Earth and we're used to the acceleration due to gravity at 10 meters per second squared. And so when you multiply 1 kilogram, the mass, by that acceleration of 10 meters per second squared, you get 10 newtons of force. And that is its weight, because that was due to the force of gravity. And that's only true here on the surface of the Earth. The weight would be something different on the moon. because the acceleration due to gravity is different. The mass would be the same. Nah. Nope. All right, go. A mass is added to a pushed object. Its acceleration does what? So you push something, it moves. Push it again, but it has more mass now. What happens to the acceleration? The same thing is true if you want to think of it as you're pushing something, you're exerting a force on it and making it accelerate. Put more mass on top of it and keep pushing at that same push. Something's going to happen to the acceleration. What? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay. I can see as you respond, and that's the highest it's ever gotten yet, so I figure you're all in that are wanting to participate today. 88% think it's B. You think it decreases. See? You guys are getting this. That is absolutely correct. And Newton's second law, if you get stumped conceptually, reminds us of that. F equals ma, force equals mass times acceleration. You increase the mass, the acceleration has to go down to keep the force the same. Some people do think better mathematically. All right, enough of those for now. Sorry. We have these valves over here and the cord always catches. Drops the mic and makes his ears ring. I love the example in the book, so I want to reiterate it. They got a guy punching a punching bag and then like a piece of paper, I guess. Back to Newton's second law. You punch this as opposed to punching this. Might sound like a trick question. Which one can I hit harder? Harder is not, we haven't, physics term, that's why it might seem a little tricky. I'm not trying to trick you, but you see what I'm getting at? Which one can I hit harder? You think the ball, raise your hand. Anybody think this? How come? You can follow through. Oh, and there is some truth to that. Anybody else who thinks this one's harder? Be brave, because I haven't told you if you're right yet. Oh, yeah, I didn't give that option. Is it the same? Who thinks it's the same? Good point. How come?
Because you're exerting the same amount of force on it. I'm not sure if you find it harder.
Yeah, the only thing that's a little tricky is harder is a little vague. What do you mean by harder? That's the only technical thing. So I'll specify, be more specific. The force that these feel, assume it's your face. Which one will hurt more? If your head is this big and heavy and I hit you, or with my same punch, I hit your face, but your face is light and flimsy like this. Now which one do you think will hurt more? Does that change your answer?
Yes.
Okay, who thinks this would hurt more? Who thinks this will hurt more? More of you. And the same? Who's still voting the same? Okay, they're good. I'm glad I'm doing this then. We're divided. Okay, the key here, I'm going to do the same punch. So I push that. I exert a force on the ball. And the ball exerts a force on me that's more or less or equal. Right, so we feel the same thing. How about this one? When I hit it, the force it feels compared to the force it exerts back on me, how do they compare? They're balanced. This is Newton's third law. So we just have to figure out, is this force any different than this force?
You can't put as much force on a piece of paper.
Well, you're saying I can't put as much force on this. Explain further. Please.
I can't remember. I know
He's remembering reading something. He thinks that you can't put as much force on this one. So
Which means it won't give you as much force back into your fist because they both.
that's true. If I can't put as much force on this, then it won't push back as much either. Yes?
Force equals acceleration times mass, right?
Force is mass times acceleration, yes.
So if you had the less mass, that one weighs less. So you have to apply less force, or it'll equal less force because the mass is smaller. Whereas with that one, the mass is more. So you get the same acceleration, the force is smaller.
That's very logical. Repeat. F equals ma. The thing with more mass will be accelerated less, given the same force, and vice versa for this. So I'm curious, which one do you think is receiving more force? Because it takes more force to make it move as much. Gotcha. Yes?
The force between the two is going to be equal because you're putting the same punch, and since the medicine ball is significantly heavier than the coffee filter, it's not going to accelerate as much.
That is true as well. Because this has more mass inertia, it won't accelerate as much. You can see that, as opposed to. That is true. This is great. I refer you to page 67 when you make a note to reread this at some point. There's a picture of him punching the punching bag in the paper. Just the caption on it will give us the answer. He can hit the massive bag with considerable force, but with the same punch, he can exert only a tiny force on the tissue paper in midair. So I might be exerting, using the same amount of energy and doing work, but that's after the test. It's the same punch. But the actual force between these two, if we could take a scale and measure that force, like when I hit them, the forces between are less in this case than this one. Because just as it goes into it's inertia. It can't resist it. This can only push back so much before it gets moving. It doesn't have that mass and inertia to resist it. So it overcomes it quicker. Its motion changes sooner. It can only push back yay hard force. So even though I might have potential energy stored up to provide more force, obviously, the actual force felt between these two is less because it can only resist so much. And my whole bottom line with all of this is you cannot have one force without the other. Again, they're two, they go hand in hand. That's the action-reaction pair. This on that back. You can't have an isolated force. And that force can only be as much as one of them can provide. And if I hit the wall, that's going to hurt. Because it can push back with more force than I can provide. But this can't withstand it, so it gives. So there's a hand over here.
Does that mean that at some point when Newton's third law is always true, and then there's a point when I guess you exceed it just because the issue is...
It seems like an exception to Newton's third law sometimes. Yeah, the point is, Newton's law holds for both cases. It only says that when I hit this, the force on it is the same as the force of it back on me, equal but opposite in direction. It doesn't tell you what the magnitude is. It just tells you that the two are the same. And it says the two here are the same. But it doesn't say that this force has to be the same as that force. And that's what's the confusing part here. Do you follow that? Action-reaction pair here equal, action-reaction here equal, but they don't necessarily have to be equal to each other. That's what we're getting at. What I learned practically out of this, if somebody's going to hit you in the face, don't be stiff. If you're like this ball and try to resist it, boom, try to hold still, it's going to hurt more because you're providing more resistance. Thus, you can provide more force. And if he can hit you with that same amount of force, that's going to be the magnitude of that action-reaction pair. But if when he swings to hit you, you kind of give a little, then you don't resist it as much. He can't impart as much force onto your face if your face can't match it. You know what I mean? It's one reason people go like this. Doesn't hurt as bad. There's other reasons. That's after the test. See? It all builds. Isn't this great? You're like, oh, great. Other queries about this? That's why I thought this was a great example.
So it doesn't change anything about Newton's third law, it's just...
Right, yeah, I wanted to specify again for redundancy. Newton's third law says for every action there's an equal but opposite reaction. And it's true for this one too. But it doesn't say just because I use the same fist that it's going to be, has to be equal always. Depends on what you hit. What's reacting. Okay. All right, let's shoot out some examples. Let's you guys help me. Some action-reaction pairs. Just throw out a force. Something pushing on something or something, and let's see if we can find the reaction. Propeller on a boat. Okay. Give me one force. One body on another.
The propeller is pushing against the water.
Okay, so the propeller exerts a force on the water. What's the reaction? Water must push on the blades of the propeller, which are connected to the boat and help you go. Great. Next.
Football, kicked by the football.
Yes. So a foot kicking, exerting a force on a football. Great. Reaction?
Yeah, the reaction is ball pushes back on the leg.
Ball back on the foot. Yeah. And that's why when you kick if you came up and kicked this medicine ball, it hurt. Because it's got more mass and inertia. It doesn't want to be accelerated for the same force coming in. And it is able to apply more force back on your foot. And so that action-reaction pair would be greater the more massive the thing is. Good. More. Sprinting. Okay. What on what? Right. You push off on the ground pushes back. If you guys, at some point in your life, when you're bored, sit around, you're stuck in transit or something. Imagine what the world would be like without friction. As much as we complain about it, and physicists like to ignore friction to make calculations easier, this world would stink without friction. One, you wouldn't be able to walk. Couldn't drive a car. Couldn't use a pencil. Start thinking of all the things, that friction as a reaction. If you can't get that force, then you can't push on it, it can't push back. You can't get propelled. There's a lot in Newton's third law, action-reaction, the propel. We had the propeller, hence the name, and I got a few demos for that. Give me one more.
I'd like for you to explain what happens when you jump up on the table.
Oh, when I jump up on the table, because I like doing that, don't I? Is this for the friction or an action-reaction pair? Is this for an example of if friction weren't here or action-reaction pair?
Well, I was using it as, thinking of it as action.
Good. I'm like, okay, there's several going on here. What happened first? I pushed on the floor. Reaction? The floor pushed back. Not gravity. That's a different one. Earth's pulling me down, I'm pulling it up. But what got me up here was me pushing on the floor with my muscles and it pushing back.
But also you push on the table with your arms.
And it pushes back. I'll give you that one. Yeah. And,
That makes it look so easy.
and the trickier one, how about now? What's the action-reaction forces? Your clues, there's two sets going on right now.
You're pulling on the earth, there's pulling on you, your weight is pushing down the table pushing back.
He's right. We have the earth trying to pull me down, I'm trying to pull it up. One pair. And the other is, because it's trying to pull me down, sure, I'm running into the table. So I'm pushing on the table pushes back. Reaction. Good. Yeah, my wife actually, she wishes she could do this, but yeah, that's the key. Use your arms and it's much easier. You can just kind of Notice the, oh, what the hey, the center of mass. If you try to just stand here and whoop, go up, I'm not even going to try. It's hard. And a lot of people try to stay all straight too, and they're all like, whoa. My center of mass is about here. That just means if I could concentrate all my mass into one spot to say Earth is trying to pull on what part of my body, you could approximate it as roughly here. Well, that's already above the table. So you can minimize your work if, this is a side note by the way, if I try not to lift my center of mass, maybe just my legs. But if my legs are coming up, maybe I can go down. And you do that instinctively. Well, I do. Trying to watch the cable. You just kind of watch my center of mass. Whoop. I really only raised it this far. Then I just use my muscles to stand up. I didn't have to jump that high. And it makes it easier. Anyway. So let's do a reaction. This is my daughter's favorite. I keep expecting it to. About a third of them pop on me. All right, I'm going to let go of the balloon. You've all done it, right? This is a cooler balloon. And what's going to happen? And it's going to go. Now explain the physics why, because you know now. Say again? Concentration gradient. Yeah, that sounds good. What's that mean? Yeah, there's imbalance of pressure. And that's going to get the air moving in the first place. Then what?
Well, it's just like a rocket. It's taking all the energy from the air trying to escape and pushing it through one point. And since the air is going out like that, the remaining air that's already out is going to push back.
Well said. I didn't expect you to understand the pressure part because we haven't talked about fluids yet. But you guys know that. It gets stretched. It's under pressure. That's common. You know the air is going to come out. Point is, the balloon's going to exert a force on the air pushing it out. Well, Newton comes along and says, well, then the air pushes back on the balloon. And if there's a force on the balloon, it can accelerate it. It was lame. Yeah, we'll do it again, see if it'll go up this time instead of... Can't necessarily control it. Not this one. This was an initial problem with beginning rockets, by the way. Okay, let's go to the moon. So then you have to worry about guidance systems and fins and all that kind of stuff. But what actually makes it move is propulsion, Newton's third law. Let's do, this is my indoor version of a water rocket. How many have done water rockets before? They're fun. They make a big mess, so I'm only going to do a little version. But rockets have fuel. In this case, the water is going to be the fuel. You seal it off. I pump it up to increase the pressure. It's trying to leak. Let's just... You're all like, woohoo. Well, I didn't want it to smack the thing and soak them. That's why it's the indoor. But again, the pressurized air, so it wants to move out. Well, what's in its way? The water. So there's your force. The rocket is pushing the water out. Well, then the water must push back with the same force on the rocket. Who has more mass? The rocket. So who accelerates less? the rocket. And just think how fast rockets go. So if the rockets can accelerate that much and be that massive, think how fast the little mass of gases shooting out the hind end are going. Let's do that one. I think you'll like this one a little better. So I got some alcohol. I'll put in here. Another one. Coat the inside of the bottle with methanol. It's that type. Because the vapor is what ignites, and I want more vapor inside. So if I coat it, it'll evaporate quicker. And then there's a small hole in the cap, and I'm going to stick this up near the outside of that hole. It'll excite the gas, and you explain Newton's third law. What happens next? It's a 2-liter plastic bottle.
The gas is going to combust and expel energy out the back.
Right. Okay, bottle force on gas out. Thus. That's right. And this is light gas, mind you. It's teeny mass. That's better. Zesty. So I'm still impressed that the bottle accelerates that larger rate. So the small mass of the gas must really be cruising. And it is. That's why it works. Again, that was a force of bottle on gas, gas on bottle, same. So big mass, little acceleration, little mass, big acceleration. But if you can adjust these enough to still make the big heavy space shuttle rocket accelerate enough to make it out of our atmosphere. Impressive. Newton's third law. Any question? So look in life, especially this weekend, for things that recoil. I bet a lot of you can already guess other examples of things that recoil. Give me one. A gun. See, that's everybody's first answer. It's great. Well, that's it. If you're exerting a force to accelerate a tiny little mass of a bullet out at a high velocity, it's going to take a lot of force. Well, you're going to feel the same force back on you, and you get that kickback. That kickback is you feeling the reaction force. And it's the same force, but you're more massive, so you don't accelerate as much as the bullet. I'm sorry. A car. Give me more. How so? In which way? He says you're in a car. Let's say you're at stop, and you just floor it and accelerate. What happens to you? Back in your seat. Right. Right. That's a great example. It's not for Newton's third law, though. Which law is that? Yeah, it's not an action-reaction pair. It's actually you feel that because of inertia initially. It's first law. You're at rest, and when you want to stay at rest, and that's a great example, you exert some force on the car, and there's a reaction there, and it starts accelerating forward. Well, you don't want to yet. You stay put while the car moves. So what do you feel? You feel the back, your seat, run into you. It feels like you're being thrown back, but it's because it came up to meet you because you're staying at rest. Now it exerts a force on you. It pushes on you, you push on it, and that's what you feel. That's the third law. Yeah.
On a hose, like when you accidentally let go of the hose and it goes.
Oh, water in the hose. That's a good example. Yeah, you're spraying with a hose. The hose pushes the water out, but the water's pushing back on the hose. So if you let go of it, yeah, it just starts kind of like the balloon. Good. Quiz time. I'm going to prompt you on this one. Get that clicker out. I'll go ahead and open polling and pose it to you. This is a fan cart. It blows air this direction. And it's free to roll. So I'm going to put this fan right here, the sail, sorry, and I'll turn it on. The question from your perspective, your side, which way will it go? To the right, to the left, or not at all? So A, to the right, to your right, to the right. To the left, C, not move. This works, I turn on the fan, it blows air that way only. I don't feel anything. So yeah, when this fan turns, it blows air that way. You got some votes? 44. 44. Yeah, I admit, this one's meant to be more of a thinker. Well, I hope. Again, I don't expect you to be right yet. 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, come on, there's only 2 of you left. There you go. Okay, we have 46% for B and about 30% on the others. I'm rounding. So it's kind of split. So now, this is the fun part. Some of you were. Try to convince your neighbor. Tell them your reasoning, and let's see if people switch. Vote again. Start voting. Oh, we got a lot more votes to get in. Yeah, it's open. Vote again now. I want to see if it's changed. I've learned you guys listen to each other more than you listen to me about some physics, so. 8 more of you. Come on, make a decision. It's all right. That's why I like the clickers. It's anonymous. Well, I get to see, but I'm giving you credit for taking. All right, 10 seconds. 10. Oh, yeah. Yeah, if you do it again, it supersedes whatever. When I close polling, it'll take whatever was last entered. There's one more person I know hasn't. 5, 4. All right. Curious. All right, we got a few more for B to the left, less for A, and they shifted over to C. So most of you think it's going to move that way. And the next big chunk think it's not going to move. You ready? Side note. Which way is it accelerating? But it's moving that way. Good. Perfect answer. So, you're right. Even though it's moving that way, it's still accelerating that way. All right. So, action-reaction pair here. The propeller pushes on the air, so the air pushes back. Equal and opposite force. The air is obviously moving faster, accelerating more, this less because of the masses. Okay? You add that. That is still going on, what we just saw. That's still going to happen, right? It's going to push on the air. But what else happens? Air is going to hit the sail. Okay, air exerts force on sail that way. What's the sail do? Pushes back on the air. How do the forces compare? Okay, is that what you guys were reasoning? Well, if it's not perfectly level, it'll go any direction. So it doesn't move. So you have this action and reaction going on, you have this action and reaction go on, and they're the same because, in this case, this force pushing on the air pushes on the cart. That way. Well, the cart has a certain mass. Well, that same air with the same force is pushing this way at the same time, and it's connected to the cart. It has the same mass, so it's the same effect. So they're essentially negating each other. Now we have action-reaction pair, action-reaction pair, but when we want to know the motion of the cart itself, we have to look at only the forces on the cart. So in this case, air pushing back. In this case, air pushing that way. And so they negate each other. It's in equilibrium. The net force is 0. It doesn't accelerate. Yes?
Would it still not move if the thing was in front of it, like directly like not next to it?
If it was over here?
Yeah, or you could say like right in front of it.
Like that?
Off the cart, but like right in front of it.
So not touching the cart. You ready? Like that? This brings up an important point real fast. Rockets work in space, don't they? What propels a rocket? The rocket pushes the fuel out, the fuel pushes back. Does it need an atmosphere? Yeah, having a wall here that the air pushes on doesn't help. That's not what propels the cart. It's the air reacting back on the propellers. Propellers pushes the air pushes back. That works whether I have this or not. Reverse, you know what I mean. Not. It still propels. This needs air, of course, but a rocket doesn't. It's just because it throws things out, it's tiny. It doesn't need a wall. Yeah. If there was a piece of paper here attached to the cart? Oh, if it could stay fixed and you know, once the air fills the cell and it stays rigid, it would act just like this sail. If it could collapse like this, it wouldn't be effective. So a sailboat, the wind blows in, hits the sail pushes back on the air. Yeah.
So it seems to be the weight in
Oh, the sail when you, yeah, does this need to be lighter? Short answer, no. Obviously, this is fairly heavy. This is heavier. It's more just at some point, if this were lighter, maybe it would move then. That's what you're getting at, because this is heavy? Oh, some people know. Well, if something, any type of sail is attached to it, so it's part of it, then this pushes on the air, the air pushes back. That's propelling the cart that way. One force on the cart for that way. That same air, though, is exerting the same force on a sail attached to the cart, trying to make the cart go that way. So as long as the sail can capture that air, it's going to feel a force that way also, which will match the force it's trying to propel it that way, regardless of its size, shape, mass, or whatnot. Now, granted, if this gets too heavy, period, it can't propel it in the first place. Yeah. And I do, lest you guys start getting smart on me, sailboats, they can curve, and you can get lift that way by deflecting air, but I'm not going there yet. Another hand?
If you were trying to figure the net force, which direction is the gravity pushing when there's no sail? Not gravity, friction.
Which way is friction? If it's not, it's nowhere. And without this, with the sail or without? Let me get it. Without. Do you have a guess which way friction is first? Yeah, it's the table pushing on the floor. It's the interaction there, or the table, on the wheel, sorry. The wheel's trying to come along and go like this. Do you see that? It's trying to rotate and push that way. So actually the friction between the table and the wheel is that way. Yeah. That can seem confusing because, if I push this, friction's that way. It's opposing the direction. Well, with a wheel, you have to realize the wheel's turning. And if the wheel's trying to go like this to make you go that way, the wheel's trying to push that way where it's in contact. So the frictional force is actually that way. But there's other things going on we haven't discussed. Good. Other questions? Does this, yeah, okay. I said you don't need it attached, or period, to propel. But does putting it here make it go better? No. No. Because the air comes and hits this, right? So the air is exerting the force on this, trying to make this move and change its motion. Well, it's attached to the wall and the arm, so it's trying to make me move. Can it like reflect back and push on the thing? Technically, yes. Is it significant? Not really. Not really. And it would only work when you're really close, and as soon as you get... There is a ground effect, and that's where it's noticeable. You have to be right there. It might be more conspicuous with water. If this was shooting water out of a hose and it hit this and bounced back and then ran back into the cart, then something else is going on. That's an additional force, yes. Air kind of...
I was just going to say, if people are really interested in the whole van sail thing, Mythbusters did a whole episode on it.
Oh, you got a lot of Mythbusters. Good. All right. I won't keep you. If you've got other questions coming up. Have a good weekend.